Hi everyone, my name is Bokyeung. I will introduce how to sample order-aware consistency for low-resolution facial expression recognition. This is the contents. In real scenario, we can see multi-scale low-resolution facial images. To recognize the facial expression in practical scenarios, we have to develop facial expression recognition model for multi-scale low-resolution images. Consistency learning technique is a good choice to develop robust deep network model that accommodate input variations. Consistency learning encourages outputs from augmented input to be close to output from the original input. However, when utilizing consistency learning, we employ random downsampling operation to train facial expression recognition for multi-scale low-resolution images. Due to downsampling, tears and fine eye wrinkles disappear, resulting in an appearance resembling an angry face. Consequently, the prediction of the facial expression recognition model is anger rather than the original label set. We define how to sample as augmented samplers that networks struggle to extract expressive features. Previous consistency learning encourages how to sample to be close to original sample. The how to sample is forced to closely resemble the original sample when employing the previous consistency learning. Then how to sample is treated similarly to the original samples in feature representation. This impedes the learning of a generalized model. To address these challenges, our goal is to enable the network to learn linear behavior on feature representations from multi-scale low-resolution images. And after sufficient optimization, how samples are predominantly positioned at the periphery of the class sample distribution, unlike the previous consistency learning. The proposed method consists of combined attention consistency and label distribution learning. Input images are original image, low-resolution image from downsampling operation, and horizontally flipped low-resolution image. We can obtain 3 attention maps by using class activation map technique and 2 logits by original and low-resolution images. In order to learn linear behavior on feature representations from multi-scale low-resolution images, our proposed combined attention consistency is to align attention maps from multi-scale low-resolution images with appropriate target attention maps. First, combined attention map is generated by linearly interpolating of 2 attention maps from original and flipped low-resolution images. Secondly, combined attention consistency loss function minimize the difference between attention map from low-resolution image and combined attention maps. Label distribution learning is utilized to tackle ambiguous sample generated by downsampling augmentation. Target distribution is generated by linearly interpolating of a logit of original sample and on a label. And then, a cross-entropy loss function is employed to learn target distribution. We determine whether the input image is classified as a hot sample by assessing its classification difficulty. If the classification results of low-resolution image is not the same both classification results from original sample and label, we consider low-resolution image as hard sample. Total loss function consists of cross-entropy loss function for original image, attention consistency loss function, and label distribution learning loss function. And this is adaptively applied depending on whether the low resolution input is a hard sample or not. When low resolution image is hard sample, we remove the label distribution learning term to prevent overfitting. We evaluate our proposed method on 3 datasets. To train the model for multi-scale low resolution image, we set downsampling ratio 1 to 8 times. HSAC is our proposed method. Our method outperforms previous method by a large performance difference at all downsampling ratio. Also, the proposed method outperforms state-of-the-art methods in original facial expression recognition performance, even though it was trained for multi-scale low-resolution images. Model with augmentation technique failed to capture the discriminable regions across all downsampling factors. A model with previous consistency learning completely faltered in classifying the facial expression at 8 times downsampling ratios. In contrast, we can see our proposed method precisely capture the most discriminative facial area. And we visualize feature distributions for all downsampling factors using TSLE. Left figure denotes model with previous consistency learning, and right figure is model with our proposed method. Hard samples are denoted by black dots. In left figure, we can see that hard samples are positioned amid the distribution of class sample. In our case, hard samples are only placed at the periphery of the class sample distributions. The result suggests that controlling hard samples is important for creating discriminative feature distributions and a generalized model for multi-scale low-resolution facial expression recognition. Thank you for listening to my presentation.